What if the most significant archaeological finds of the 21st century are not interred within the Earth's crust, but are instead hurtling through the cosmos over our very heads? For the majority of human existence, I operated under the belief that Earth was in a state of magnificent solitude, divided from other cosmic bodies by such immense gulfs that any substantial interstellar discoveries were out of the question. Then, in 2017, an object careening through the void at 87,000 kilometers per hour utterly demolished that notion for all time. It was succeeded by more, each one more enigmatic than the one before. These celestial travelers from beyond our star system exhibit behaviors unlike anything within our solar system. They gain speed without any observable means of propulsion. They preserve their structural soundness over voyages lasting millions of years. They appear from arbitrary points in the sky with a frequency that is causing statisticians to reevaluate the very principles of probability. This evening, as 3 Atlas makes its nearest pass to the Sun, we will learn why this particular visitor elevates Oumuamua from a celestial oddity to the inaugural element of a considerably vaster enigma. Prior to our shared embarkation upon this celestial enigma, I would appreciate it if you could share in the comments your location on the globe and the current time where you are. And if you truly appreciate my work here, I invite you to subscribe for your regular infusion of profound cosmic puzzles. Now, brace yourselves. We shall commence. Music. Envision the scene. It is the stroke of midnight at the Halakala Observatory in Hawaii. The only audible stimuli are the low drone of cooling systems and the faint clicking of storage devices cataloging terabytes of stellar information. Astronomers gaze at monitors displaying merely minuscule specks of illumination set against the boundless dark. Suddenly, an object shifts, an object that has no business being there. On most evenings, the cosmos adheres to foreseeable arrangements. Stars maintain their celestial coordinates. Planets follow their primordial trajectories. Even space rocks and comets move in accordance with gravitational cadences that have been constant for eons. Yet on October 19, 2017, the universe presented something completely new, something that would force a revision of our comprehension of what traverses the space between stars. The Pan-STARRS telescope recorded a solitary image that altered the entire paradigm. A speck of light traveling at a velocity it had no right to possess, charting a course that violated the core tenets of celestial mechanics. This object was not held in the Sun's gravitational field like every other body in our solar system. This traveler was merely passing by, as if it had an appointment elsewhere. In a matter of hours, computations confirmed the unbelievable. The object's path was hyperbolic. Not the gentle curve of a comet or asteroid, but the acute trajectory of something that originated from another place and was bound for another place yet. Its velocity in relation to the Sun was 26 kilometers per second, a speed greater than anything created in our own stellar vicinity should be capable of. The astronomical world was thrown into a state of controlled pandemonium. Urgent observation proposals inundated telescope networks across the planet. Every scientist desired a glimpse of this cosmic outlier before it disappeared back into the void between the stars for good. Social media platforms erupted with conjecture. News presenters fumbled with its Hawaiian designation, Oumuamua, which translates to scout or emissary from a distant place, arriving first. However, this is where the narrative becomes truly captivating. As observatories around the globe directed their focus toward this interstellar traveler, they found something that flew in the face of every preconceived notion about what such an object should be. This was not the generally round mass of stone and ice that they had anticipated. The luminosity of Oumuamua fluctuated by a multiple of 10 as it spun through space, hinting at a protracted form unlike anything I had previously seen. Picture a celestial cigar, maybe 800 meters in length, but a mere 80 meters in diameter, rotating end over end as if hurled by an unseen titan. Its exterior reflected solar radiation in a manner that implied either a highly peculiar makeup or a non-natural genesis. A few scientists quietly suggested what their colleagues were afraid to articulate. What if this was not a natural object? The inquiries proliferated more rapidly than the explanations. How could a body withstand a journey between star systems without being disintegrated by cosmic rays and micrometeoroid collisions? What accounted for its peculiar configuration? And most perplexingly, why did it appear to accelerate marginally as it receded from the Sun, despite displaying none of the gaseous emissions that typically cause such phenomena in comets? Dr. Robert Varick, the astronomer who initially identified the anomaly, later recounted the instance of its discovery. I examined the information and concluded that the computer must have made a mistake. Objects simply do not move in this manner within our solar system. But the computer had not erred. The cosmos had provided something without precedent. As Oumuamua tumbled away from the Sun, gaining velocity as it went, it left a legacy of more questions than answers. Was this visitor a piece of a far-off world, cast out billions of years prior by gravitational turmoil surrounding an alien star? Or was it something else altogether, a technological artifact crafted by intellects I could not yet fathom? The scientific mainstream swiftly coalesced around naturalistic interpretations. Comets are frequently ejected from their home systems. Gravitational interplay with massive planets can propel smaller bodies into interstellar space at immense speeds. What I had observed was likely just the first instance where I had been fortunate enough to see one of these cosmic wanderers traversing our local space. Yet fortune seemed an insufficient reason for the timing. Humankind had been methodically observing the heavens for under a century. The likelihood of spotting such an infrequent visitor during this brief period of our technological infancy appeared almost vanishingly small, unless, of course, these travelers were not as uncommon as I had believed. While Oumuamua sped beyond the observation range of our most powerful telescopes, a fundamental change had occurred in the field of astronomy. Survey initiatives started allocating more resources to the search for comparable objects. New detection software was created with the specific aim of identifying the characteristic signs of interstellar movement. Funding bodies, once dubious of speculative research, suddenly began to greenlight projects focused on the study of visitors from outside our solar system. The universe had presented me with something I was not ready to witness. An object that was not part of any star system, that followed no recognizable orbit, and that displayed characteristics that tested my comprehension of natural phenomena. It showed up without warning, guardedly shared its mysteries, and left with the same enigmatic intent that had brought it to us. As Oumuamua vanished into the celestial abyss, heading towards the constellation Pegasus at 38 kilometers per second, it imparted a sobering truth to humanity. I am not alone in the void between the stars. Objects, whether natural or otherwise, navigate the galactic emptiness, bearing the chronicles of remote worlds and ancient cataclysms. The emissary from afar had conveyed its message, even though I was still in the process of learning to decipher it. What was clear was that Oumuamua would not be the last of its kind. The expanse between the stars was not the barren void I had envisioned, but a thoroughfare used by sojourners from all corners of the galaxy. And if masses of rock and ice could withstand such journeys, what other entities might be out there, drifting among the stars, awaiting the opportune moment to pass through my cosmic backyard? The question lingered in the atmosphere like the smell of rain before a downpour, charged with potential. As one astronomer remarked, "I have been observing the stars for my entire history, believing I was isolated in this part of space. Now I know differently. The galaxy has been observing me all this time, dispatching its messengers when I was finally prepared to see them. The era of interstellar visitors had commenced." Part 2. The day the firmament was altered. Oumuamua's initial sighting. The shift in our comprehension was not a slow process. It transpired in a single instant, recorded by an automated telescope on a Hawaiian mountain and analyzed by algorithms that had been performing the same computations for years. October 19, 2017, 2:20 in the morning local time. The Pan-Stars. One telescope on Halakala finished another standard sweep of a celestial region in the constellation Cancer. The resulting image showed approximately 60,000 stars, the majority of them so far away that their light had journeyed for millions of years to arrive at that moment. Amid these ancient photons was something entirely different, a minute trail of reflected sunlight from an object that had never been a part of our solar system. The finding nearly went unnoticed. The automated detection software identified the object as a likely near-Earth asteroid. This was not remarkable in itself. Our solar system is filled with stony fragments remaining from its formation 4.6 billion years ago. The majority of these bodies follow predictable elliptical paths, sometimes coming close enough to Earth to attract the notice of planetary defense initiatives. But Dr. Robert Warwick, while examining the night's findings at the University of Hawaii, observed something peculiar. The object was traveling too quickly and in an incorrect direction. Preliminary computations indicated it was arriving from beyond the solar system, a prospect so improbable that most astronomers would have presumed a calculation error. The object received the designation A2017 U1, a provisional name that gave no hint of its remarkable character. Within 48 hours, further observations verified the incredible. This traveler was on a hyperbolic course with an eccentricity exceeding 1.0. In the terminology of orbital dynamics, this signified it was not gravitationally bound to the Sun, but was merely transiting on its way to another destination. The astronomical community acted with an unprecedented sense of urgency. Emergency observation proposals were sent to every major telescope installation on the planet. Time that was typically reserved for long-term research was rapidly reallocated to monitor this celestial intruder before it vanished permanently. The Hubble Space Telescope, the Very Large Telescope in Chile, and the Gemini Observatory all trained their sights on a visitor that would be observable for only a few weeks. What they found contested basic beliefs about the characteristics of interstellar objects. Conventional models suggested that material expelled from other star systems would be similar to the comets and asteroids in our own, generally spherical, made of common combinations of rock and ice, and perhaps a few kilometers in diameter. Oumuamua met none of these criteria. Its brightness fluctuated by a factor of 10 over an 8-hour rotational cycle, indicating a highly elongated form. The most probable interpretation was a cigar-shaped object approximately 800 meters long and 80 meters wide. This aspect ratio was unlike any natural object ever seen in our solar system. The more unusual it appeared, the more critical the observations became. Ground-based telescopes monitored it without interruption, gauging its rotation, composition, and path with unparalleled accuracy. Radio telescopes scanned for any potential artificial transmissions. Even SETI researchers contributed to the effort, although they detected only the quiet of interstellar space. Then the acceleration anomaly emerged. As Oumuamua receded from the Sun, it started to increase its speed slightly, not by a large amount, but enough to be measured by precise astrometric observations. This non-gravitational acceleration is typical for comets, resulting from jets of gas sublimating from their surfaces as they heat up near the Sun. But Oumuamua displayed no indications of such outgassing. There was no visible coma, no tail, and no spectroscopic proof of water vapor or other volatile substances. The enigma grew with each new piece of data. Its surface had a distinctly reddish hue, consistent with organic materials that had been exposed to cosmic rays for millions of years. Yet, despite this ancient appearance, the object seemed structurally sound, with no evidence of the fracturing and wear expected from eons of interstellar travel. Dr. Alan Fitzsimmons from Queen's University, Belfast, summed up the scientific community's confusion. Every time I aimed a new instrument at this object, it grew more peculiar. I kept anticipating it would act like a standard comet or asteroid, but it consistently deviated from the expected behavior. The media reaction was swift and widespread. In a matter of days, Oumuamua was featured on front pages across the globe. Conjectures varied from the scientifically plausible to the wildly speculative. Was this a piece of an exoplanet hurled into space by a cosmic event? Could it be an alien probe intentionally dispatched to investigate our solar system? Or was it simply a type of object so uncommon that I had never seen one before? The scientific establishment recommended prudence, stressing the need for exceptional evidence for exceptional assertions. Natural explanations, though admittedly imperfect, were considered more likely than artificial ones. Perhaps Oumuamua was made of unusual substances that accounted for its strange characteristics. Maybe it was a fragment of a larger body that had been shaped by ages of cosmic impacts. But the questions lingered. If interstellar objects were prevalent, why had I never found one previously? Our asteroid and comet surveys had been active for decades, documenting hundreds of thousands of solar system bodies. The chance of finally detecting an interstellar visitor seemed incredibly low. Unless such objects were far more plentiful than anyone had assumed, the implications were immense. If Oumuamua was a typical example of interstellar material, then our solar system was being constantly visited by fragments from other star systems. I existed within a massive flow of cosmic matter, most of it too small or too distant to be detected with my current technology. Every year, possibly every month, pieces of alien worlds might be passing through my cosmic vicinity, carrying the chemical fingerprints and physical traits of their origins. As Oumuamua continued its voyage toward the constellation Pegasus, accelerating beyond the range of Earth's most powerful telescopes, it left in its wake a changed scientific field. Funding bodies suddenly began to support research into interstellar object detection. New survey telescopes were developed with the explicit purpose of finding and tracking visitors from other star systems. The visitor had been under intense scientific observation for just 11 weeks before it faded into the cosmic background. In that short time, it had managed to challenge my understanding of planetary formation, interstellar chemistry, and the rate of material exchange between star systems. It showed that the space between stars was not the empty void I had imagined, but a complex realm inhabited by travelers from every corner of the galaxy. Perhaps most significantly, Oumuamua demonstrated that I was not as isolated as I had thought. The solar system was not a self-contained system shielded from external influences by the vast distances between stars. I was a participant in a galactic ecosystem, receiving visitors and likely contributing my own debris to the interstellar medium. As the object moved beyond Jupiter's orbit, traveling at 38 kilometers per second relative to the Sun, one reality became undeniable. Oumuamua was probably not one of a kind. If the galaxy housed billions of planetary systems, each one occasionally ejecting material into interstellar space, then such visitors might be more common than I had ever conceived. The sky had not merely changed on October 19, 2017. My entire conception of my place in the cosmos had been transformed. I was no longer alone in this region of space, waiting for signals from distant civilizations. The universe was actively bringing samples to my doorstep, bearing messages written in the language of physics and chemistry instead of radio waves. The first interstellar visitor had left, but its influence endured. Somewhere in the darkness beyond Pluto's orbit, Oumuamua continued its billion-year journey to the stars, carrying with it my questions and my newfound humility about what else might be traversing the space I call empty. Part 3. The Impossible Configuration. The figures were nonsensical. That was the initial observation of every astronomer who attempted to create a model of Oumuamua's remarkable light curve. Objects in space generally exhibit brightness variations of perhaps 20 or 30% as they rotate, presenting their different sides as they move through the void. But this interstellar traveler was operating under a different set of principles entirely. Every 8.26 hours, Oumuamua would become barely perceptible, then increase in brightness to 10 times that level, and then dim again with clockwork regularity. This was not the gentle change of a potato-shaped asteroid or the erratic flicker of a shattered comet. This was the mark of something fundamentally distinct, an object so elongated that it seemed to defy the fundamental physics of how celestial bodies are formed and persist. Dr. Karen Meach from the University of Hawaii headed the international group attempting to understand these findings. When I first examined the light curve, she stated, several individuals proposed that there must be an error in the data processing. Objects simply do not naturally form with such extreme aspect ratios. The most cautious estimations indicated Oumuamua was at least 6 times longer than its width. More daring analyses of the data suggested an even greater ratio, possibly 10 to 1, making it more akin to a cosmic needle than a typical space rock. To provide some context, envision a football field that was only 10 yards wide. No known process in planetary science could account for how such an object might be created, much less endure the turbulent voyage between star systems. The rotation itself was another enigma. Most asteroids and comets revolve around their shortest axis, like a top spinning on a surface. This is the most stable arrangement, the natural outcome of innumerable collisions over millions of years. But Oumuamua was tumbling in a complex manner that astronomers refer to as non-principal axis rotation, essentially performing cosmic acrobatics as it traveled through space. This tumbling motion hinted at either a recent impact that had disturbed its rotation or an internal structure unlike anything in my experience. Perhaps it was hollow. Perhaps it was made of materials with unusual density arrangements. Or perhaps it had been artificially built with a specific objective. The surface characteristics only amplified the mystery. Spectroscopic analysis showed a dark reddish hue, consistent with organic compounds that had been irradiated by cosmic rays for millions of years. This lent support to the theory that Oumuamua was ancient, possibly even older than our solar system. Yet, despite this apparent age, the object displayed no signs of the structural decay expected from eons of micrometeorite impacts and cosmic ray exposure. Even more perplexing was its thermal response. As Oumuamua neared the Sun, it should have warmed considerably, potentially causing ice to sublimate and form the distinct coma and tail of an active comet. Instead, it remained stubbornly inactive, showing no evidence of outgassing despite reaching temperatures that should have vaporized any volatile substances on its surface. Then came the acceleration anomaly that turned scientific interest into genuine confusion. Precise measurements of Oumuamua's path revealed that it was speeding up as it moved away from the Sun, not significantly, but by about 0.25 millimeters per second squared. For a comet, such acceleration would be easily explained by gas jets from sublimating ice. But Oumuamua showed no signs of such outgassing. The effect was minor but irrefutable, measured independently by multiple tracking stations worldwide. Whatever was propelling Oumuamua away from the Sun was doing so invisibly, without any of the usual indicators that accompany natural cometary activity. Dr. Marco Micheli from the European Space Agency, who oversaw the orbital analysis, articulated the predicament. I am observing an acceleration that necessitates some kind of force, but I cannot pinpoint the mechanism. It is like seeing a car accelerate without being able to see its engine. Theoretical explanations proliferated like cosmic conspiracy theories. Perhaps Oumuamua was releasing gas so thin that it was undetectable by my instruments. Maybe it was composed of exotic materials that reacted to solar radiation in unforeseen ways. Some proposed it might be a hydrogen iceberg, a solid piece of hydrogen that would sublimate without a visible trace as it heated up. More unconventional ideas came from the fringes of the scientific community. Could this elongated object be a light sail created by an extraterrestrial civilization to travel on the pressure of starlight between star systems? The acceleration was in line with what would be expected from such a device, and the extreme aspect ratio would maximize the surface area exposed to solar radiation. Dr. Avi Loeb from Harvard University became the most notable supporter of this artificial hypothesis, contending that the scientific community was too hasty in dismissing technological explanations. "When I encounter something unprecedented," he stated, "I should explore all possibilities, including those that challenge my assumptions about what exists in the universe." The discussion exposed deeper frictions within the astronomical community. Traditional scientific practice requires exceptional evidence for exceptional claims, and the evidence for an artificial origin was, at best, circumstantial. Most researchers preferred to rule out all natural explanations before considering more speculative options. However, the natural explanations themselves were strained. The proposed mechanisms for Oumuamua's acceleration required very specific parameters and unusual material properties. The object would need to be made of materials never seen in our solar system, arranged in ways that defied the conventional understanding of how celestial bodies form. As Oumuamua faded beyond the detection capabilities of Earth's telescopes, it left behind a series of unanswered questions. How could an object maintain such an extreme shape without disintegrating under the stress of its own rotation? What unseen force was accelerating it away from the Sun? And, perhaps most crucially, how many similar objects might be traversing our solar system unnoticed? The visitor had given humanity its first close look at material from another star system, and that material refused to conform to the rules I thought governed the universe. It was too elongated, too stable, and too mysterious to be neatly classified among existing categories of astronomical objects. In the months after Oumuamua's departure, computer simulations tried to model its formation and evolution. Researchers suggested scenarios involving tidal disruption near massive stars, collisional fragmentation in dense stellar clusters, and exotic sublimation processes that could create such unusual shapes. None of these models offered a fully satisfactory explanation for all of the object's observed characteristics. The most candid evaluation came from Dr. Robert Warwick, the astronomer who first found the object. "I have learned more about interstellar visitors from this single object than from decades of theoretical speculation. But primarily, what I have learned is how much I do not know." As Oumuamua continued its journey toward the constellation Pegasus, tumbling through interstellar space at nearly 40 kilometers per second, it took with it my assumptions about what natural objects should look like. The messenger from beyond our solar system had delivered an unequivocal message. The universe is more peculiar than I had imagined, populated by objects that challenge my understanding of physics, chemistry, and perhaps even the distinction between natural and artificial. The impossible shape had compelled me to face the possibility that my corner of the galaxy was not as isolated or as typical as I had believed. If this was what interstellar visitors looked like, then I was clearly unprepared for what else might be traveling through the space between the stars. The cosmic cigar had tumbled away into the darkness, leaving more questions than answers, and a scientific community humbled by its first encounter with truly alien matter. Part 4. A New Cosmic Era, Preparing for the Subsequent Visitor. The scientific community's reaction to Oumuamua was prompt and resolute. Within a few months of the visitor's departure, astronomy experienced a quiet transformation that would redefine how I survey the heavens and understand my findings. Emergency sessions were held at observatories across the globe. Funding bodies that had once regarded interstellar object research as overly speculative suddenly found themselves sanctioning multi-million-dollar initiatives. The message was unmistakable. I had been caught off guard by my first confirmed interstellar visitor, and I could not allow myself to make the same error again. The Catalina Sky Survey in Arizona quickly modified its search algorithms. Software that had been designed to locate asteroids posing a threat to Earth was reprogrammed to identify the subtle characteristics of hyperbolic orbits, the mathematical indicators of objects originating from beyond our solar system. Similar enhancements were made at the Linear program in New Mexico and the NEOWISE Space Telescope. However, the most ambitious response originated from the Vera C. Rubin Observatory, which was then being built in Chile. Initially intended to produce the most comprehensive map of the universe ever made, the project's focus was quietly broadened to include a dedicated search for interstellar objects. Once operational, the observatory would scan the entire visible sky every few nights, producing terabytes of data that would be analyzed by artificial intelligence systems specifically developed to recognize visitors from other star systems. Dr. Mario Jurich from the University of Washington, who oversaw the Rubin Observatory's data management, explained the scale of the task. "I am talking about finding needles in a haystack the size of the observable universe. But Oumuamua taught me that these needles do exist, and they are passing through my cosmic vicinity more frequently than I ever conceived." The urgency was supported by simple arithmetic. If Oumuamua was typical of a larger population of interstellar objects, then our solar system should be visited by dozens or even hundreds of similar objects annually. Most would be too small or too distant to be seen, but a considerable number should be within the range of next-generation survey telescopes. Earlier projections had anticipated perhaps one detectable interstellar visitor per decade, a frequency so low that most astronomers viewed it as a theoretical curiosity rather than an observational focus. But Oumuamua's appearance indicated that these projections were off by orders of magnitude. The space between stars seemed to be much more populated than anyone had previously thought. International collaboration increased significantly. The European Space Agency expedited the development of the successor to the Gaia mission, designed to map stellar movements with unparalleled precision. NASA's Planetary Defense Coordination Office broadened its responsibilities to include the tracking and characterization of interstellar objects. Even amateur astronomers were brought into the effort with new software tools that would enable backyard telescopes to aid in the search. The technological hurdles were substantial. Interstellar objects move differently from anything else in the solar system, following hyperbolic paths that take them from interstellar space back to interstellar space in a matter of months. The windows for detection are short, sometimes lasting only weeks between when an object becomes bright enough to be seen and when it fades beyond the reach of follow-up observations. New artificial intelligence systems were created specifically to identify these unusual motion patterns in real time. Machine learning algorithms, trained on simulated interstellar visitors, learned to differentiate them from the much larger population of conventional asteroids and comets. The objective was to identify promising candidates within hours of their initial detection, allowing telescopes worldwide to promptly begin detailed observations. Perhaps more significantly, the scientific community started to prepare for the arrival of the next visitor. Oumuamua had taken astronomers by surprise, compelling them to hastily arrange for telescope time and coordinate observations with minimal prior warning. Future discoveries would activate pre-established response plans with pre-assigned observation time at major facilities and efficient procedures for international collaboration. The lessons learned were sobering. Oumuamua had been visible for only 11 weeks before it dropped below the detection limit of Earth's most powerful telescopes. In that brief period, astronomers had managed to measure its fundamental properties: size, shape, composition, and trajectory. But many crucial questions were still unanswered. The object's internal structure, detailed composition, and formation process remained mysteries. Future visitors would be studied much more thoroughly. Plans were made for rapid response spectroscopy, radar imaging, and even potential space missions to intercept particularly noteworthy objects. The Japanese Space Agency initiated preliminary research on modified solar sail technology that could potentially pursue interstellar visitors, while NASA's Jet Propulsion Laboratory explored whether existing spacecraft could be diverted to study such objects. The search extended beyond traditional optical telescopes. Radio astronomers created new methods to detect the faint signs of outgassing that might be invisible to conventional instruments. Infrared surveys were refined to spot the thermal emissions of interstellar objects that might be too dark to be seen in visible light. Even gravitational wave detectors were considered as possible tools for finding very massive interstellar objects. The implications went far beyond astronomy. If interstellar objects were common, they represented a previously unknown method for material transport between star systems. Complex organic molecules and perhaps even basic life forms might survive the journey between stars within protective rocky or icy matrices. The concept of panspermia, the theory that life might spread throughout the galaxy through natural means, suddenly appeared much more credible. Astrobiologists started to create protocols for analyzing future interstellar visitors for signs of biological material. Sterile sample collection methods were designed for potential space missions, while ground-based spectroscopy programs looked for the signatures of organic compounds that might suggest a biological origin. The search for extraterrestrial intelligence also adapted in response to Oumuamua. SETI researchers acknowledged that technological civilizations might choose to communicate through physical artifacts rather than radio signals. Interstellar space could be filled with mechanical messengers carrying information encoded in their structure, composition, or trajectory. New listening protocols were developed to scan interstellar visitors for any potential artificial signals. Radio telescopes would automatically target newly discovered objects, searching for patterns that might indicate a technological origin. Even optical telescopes began to look for unusual reflectivity patterns that could suggest artificial surfaces or structures. The transformation was remarkable to observe. A scientific field that had been mostly theoretical suddenly became intensely observational. Researchers who had dedicated their careers to modeling the hypothetical properties of interstellar objects found themselves analyzing real data from an actual visitor. The field of interstellar object science was established overnight, complete with dedicated conferences, specialized journals, and career paths for young researchers. As the months passed following Oumuamua's departure, the scientific community adopted a new routine of constant vigilance. Every night, automated telescopes scanned designated areas of the sky, their data streams monitored by algorithms trained to recognize the motion patterns of interstellar interlopers. The discovery of the next visitor was not a matter of if, but when. Behind the technological preparations was a more profound philosophical change. Humanity's connection with the cosmos had been fundamentally altered by our first confirmed encounter with material from another star system. I was no longer a passive observer of a distant universe, but an active participant in a galactic ecosystem that periodically delivered samples to my doorstep. The age of interstellar archaeology had commenced. Each future visitor would carry with it the chemical and physical signatures of its origin, fragments of alien worlds that had been ejected into the void by gravitational interactions, stellar explosions, or cosmic collisions. By studying these cosmic refugees, I would gradually assemble the story of planetary formation and evolution throughout the galaxy. The stage was prepared for the next chapter in humanity's growing awareness of its cosmic context. Telescopes watched, algorithms waited, and somewhere in the darkness between the stars, the next messenger was already en route. Part 5. Enter 3I Atlas, the Second Emissary, July 1st, 2025. The Atlas telescope at Rio Hurtado, Chile, was performing its nightly scan of the southern sky when its automated detection system identified something unusual moving against the star-filled background of Sagittarius. The object was dim, almost indistinguishable from the background interference, but its movement was clear. too fast and in the wrong direction to be a standard solar system inhabitant. Dr. Larry Deno, the Atlas principal investigator at the University of Hawaii, got the automated notification at 3:47 in the morning local time. After years of observing the skies for potentially dangerous asteroids, his team had cultivated an intuitive understanding of what belonged in the solar system and what did not. This object, designated C-2025 Non-Atlas, certainly did not belong. The initial orbital calculations were finished within 6 hours of the discovery. The findings sent a surge of excitement through the global astronomy community. An eccentricity of approximately 6.0, signifying an extremely hyperbolic orbit that began far beyond the Sun's gravitational pull. The object was approaching from the direction of Sagittarius at a relative speed of about 61 kilometers per second, making it the fastest confirmed interstellar visitor ever found. What made this discovery especially noteworthy was its timing. Unlike Oumuamua, which had been seen as it was leaving the inner solar system, 3I Atlas was detected during its approach. Astronomers would have months instead of weeks to study this cosmic traveler before it reached its closest point to the Sun and started its journey back to interstellar space. The object's designation adhered to established procedures. C indicated a comet, 2025 Nunn marked it as the first object found in the latter half of July 2025, and Atlas acknowledged the discovering survey. The 3I prefix would be added later, officially naming it as the third confirmed interstellar object after 1 Oumuamua and 2I Borisov. But 3I Atlas was already showing traits that distinguished it from its forerunners. Even at a distance of 4.5 astronomical units from the Sun, roughly the orbital distance of Jupiter, the object exhibited clear signs of activity. A faint coma of gas and dust enveloped the nucleus, stretching about 25,000 kilometers into space. This early outgassing pointed to a composition rich in volatile substances that sublimated easily as the object warmed on its approach to the inner solar system. The Gemini North Telescope on Mauna Kea was the first to capture detailed images of the new arrival. The high-resolution pictures showed a compact, blurry object with a short, thick tail pointing away from the Sun. Unlike the smooth, star-like look of Oumuamua, 3 Atlas appeared unmistakably like a comet, aligning more closely with theoretical predictions of what interstellar objects should be. Within 48 hours of the discovery announcement, the object became the most intensively studied comet in history. The European Southern Observatory's Very Large Telescope in Chile initiated spectroscopic observations to ascertain its chemical makeup. The Hubble Space Telescope was quickly reprogrammed to take the highest resolution images possible of the visitor's nucleus and coma. Radio telescopes worldwide scanned for any potential signals that might suggest an artificial origin. The scientific reaction was vastly different from the disorganized rush that had followed Oumuamua's discovery. Years of preparation proved worthwhile as pre-established observation protocols were activated automatically. Emergency telescope time had been pre-allocated specifically for interstellar visitors. International collaboration ran smoothly through established networks. The astronomical community was prepared this time. Dr. Robert Warwick, who had discovered Oumuamua 8 years prior, commented on the change. I learned my lesson from the first visitor. This time I had plans, protocols, and prepared instruments. Instead of reacting, I was actually proactive. Initial spectroscopic observations showed a surface composition dominated by silicate minerals and organic compounds, similar to comets that originate in the outer parts of our own solar system. But slight differences in isotope ratios suggested a formation environment unlike anything in my cosmic neighborhood. The object carried chemical signatures of a star system with a different metallicity and stellar evolution history than our Sun. The rotation period was measured at approximately 29 hours, significantly slower than Oumuamua's 8-hour tumbling motion. Light curve analysis indicated a more conventional shape, generally spherical or slightly elongated, without the extreme aspect ratio that had made its predecessor so contentious. In many respects, 3I Atlas appeared exactly as astronomers had anticipated interstellar visitors would, but appearances could be misleading. As the object continued its approach toward the Sun, set to reach perihelion at 1.4 astronomical units on October 30, 2025, its behavior started to show unforeseen complexities. The rate of outgassing fluctuated in ways that did not correspond simply with solar heating. Spectral lines emerged and vanished as different chemical compounds sublimated from the surface. The tail structure exhibited subtle asymmetries that hinted at complex rotation or internal structure. The discovery had significant implications for our understanding of interstellar object populations. Finding 2 such visitors within 8 years suggested they were far more common than previously thought. Statistical analyses based on detection rates and survey capabilities indicated that similar objects might pass through the inner solar system several times per decade. More fascinatingly, 3I Atlas approached from a completely different direction than Oumuamua. While the first interstellar visitor had arrived from the direction of Vega in the constellation Lyra, this new arrival came from Sagittarius, roughly 90 degrees away in the sky. The implications were immense. Interstellar space was not only populated by such objects, but they arrived from all directions, indicating a truly galactic population of wandering debris. The object's high velocity also raised questions about its origin. At 61 kilometers per second relative to the Sun, it was moving considerably faster than would be expected for objects ejected by normal planetary interactions. Such extreme velocities suggested either a very powerful ejection mechanism, perhaps involving stellar explosions or close encounters with massive objects, or a very distant origin that allowed for gravitational acceleration over vast distances. Computer simulations began to trace possible trajectories backward in time, trying to identify the object's stellar birthplace. The calculations were complicated by the gravitational influences of countless stars encountered during what might have been millions or billions of years of interstellar travel. But preliminary results suggested origins in the galactic thick disk, possibly ejected from a planetary system that had been destabilized by stellar evolution or gravitational chaos. The media response to 3I Atlas was notably more restrained than the sensationalism that had surrounded Oumuamua. The scientific community had learned to emphasize natural explanations while acknowledging the profound implications of routine interstellar visitors. Headlines focused on the object's pristine composition and the opportunity to study material from another star system rather than speculation about alien technology. Yet beneath the scientific excitement lay a growing realization of just how connected our solar system was to the broader galaxy. These were not random encounters with cosmic debris. They were regular deliveries of samples from distant worlds, each carrying information about conditions in star systems I might never visit directly. As 3I Atlas continued its approach through the asteroid belt, brightening steadily as solar heating increased its outgassing activity, it carried with it the accumulated wisdom of another star system. Its chemical composition told the story of planetary formation around a different type of star. Its isotope ratios revealed details about stellar nucleosynthesis processes that had occurred before our Sun was even born. The second messenger had arrived, and this time I was ready to listen. Part 6. The Path of the Outsider. The trajectory of 3I Atlas narrated a story composed in the language of mathematics and gravity, a tale that spanned millions of years and countless light-years of interstellar space. To comprehend where this cosmic sojourner was headed, astronomers first needed to retrace its steps, a detective narrative that unfolded across the galaxy. In contrast to the familiar elliptical orbits of planets and comets tethered to our Sun, 3I Atlas followed a hyperbolic path with an eccentricity of approximately 6. In orbital mechanics, any eccentricity exceeding 1.0 signifies an unbound trajectory, the mathematical hallmark of an object that came from interstellar space and would return there following its brief interaction with our solar system. The object's closest approach to the Sun, set for October 30th, 2025, would bring it to within 1.4 astronomical units of our star, roughly the orbital distance of Mars. This was near enough to afford excellent observation opportunities while staying far enough away to prevent the extreme heat that might completely disintegrate its nucleus. Its closest pass to Earth would happen slightly before that, at a safe distance of approximately 1.6 to 1.8 astronomical units. But it was the direction of 3I Atlas's approach that unveiled the most compelling details about its cosmic voyage. The object entered our solar system from the constellation Sagittarius, moving at an angle nearly perpendicular to the plane of the planetary orbits. This side-on arrival was uncommon among known interstellar objects and offered significant clues about its origin and the structure of the local galactic environment. Computer simulations traced the object's path backward in time, attempting to pinpoint its stellar origin. The calculations necessitated accounting for the gravitational effects of every star within several hundred light-years of our solar system, a computational task that strained the capabilities of even the most powerful astronomical supercomputers. The most probable scenario placed 3I Atlas's origin in the galactic thin disk, likely ejected from a planetary system sometime between 1 and 10 million years ago. The ejection mechanism could have been a gravitational interaction with a giant planet, akin to how Jupiter sometimes flings comets out of our own solar system. Alternatively, the object might have been set free during the final stages of its parent star's life, propelled into interstellar space by stellar winds or more cataclysmic events. Dr. Fabo Feng from the University of Hertfordshire, who led one of the trajectory reconstruction projects, described the challenge. I am trying to solve a cosmic murder mystery where the scene of the crime is millions of years old and spread across hundreds of light years. Every star in the vicinity is a potential suspect, and the evidence has been altered by eons of gravitational interference. The object's extreme velocity, 61 kilometers per second relative to the Sun, provided further clues about its turbulent past. Such speeds necessitated either a very powerful ejection process or acceleration over immense distances and vast periods of time. The former might suggest ejection during a stellar explosion or a close encounter with a massive object like a black hole. The latter implied an origin so remote that gravitational interactions with multiple stellar systems had gradually accelerated the object to its current velocity. Comparing 3I Atlas to its predecessors highlighted the diversity of interstellar visitors. While Oumuamua had approached from the direction of Vega in Lyra and 2I Borisov from Cassiopeia, this new arrival came from an entirely different part of the sky. The three confirmed interstellar objects approached from directions separated by roughly 60 to 90 degrees, suggesting that such visitors arrived from all parts of the galaxy rather than from any specific direction. This omnidirectional arrival pattern had profound implications for understanding the local interstellar environment. Instead of existing within a relatively empty bubble of space, our solar system appeared to be situated within a complex network of stellar debris flows. Material ejected from dying stars disrupted planetary systems, and gravitational interactions throughout the local galaxy was constantly streaming through my cosmic neighborhood. The galactic context provided even more perspective on 3I Atlas's journey. Our solar system orbits the galactic center at approximately 220 kilometers per second, completing one orbit every 225 million years. During its presumed million-year journey through interstellar space, 3I Atlas would have encountered the wakes and gravitational influences of dozens of stellar systems, each slightly modifying its trajectory and velocity. The object's composition offered additional clues about its origin. Spectroscopic analysis revealed a surface dominated by silicate minerals and organic compounds, with isotope ratios that differed subtly but measurably from materials found in our solar system. These chemical signatures suggested formation around a star with a different metallicity than our Sun, possibly an older star with fewer heavy elements or a younger star enriched by previous generations of stellar evolution. Perhaps most intriguingly, the object's approach angle relative to the galactic plane suggested it had spent much of its journey traveling through the galactic thick disk, a population of older stars with different chemical compositions and kinematics than the thin disk where our Sun resides. This implied that 3I Atlas might carry samples of materials from a very different era of galactic evolution. The trajectory also revealed information about the object's future after its October encounter with the Sun. 3I Atlas would begin a gradual acceleration back toward interstellar space, eventually reaching an escape velocity that would carry it beyond the outer planets by early 2026. Computer models predicted it would exit the solar system in the direction of the constellation Perseus, beginning another million-year journey through the galaxy. But unlike its inbound trajectory, which had been shaped by the gravitational influences of dozens of stellar encounters, the object's outbound path would be relatively predictable for the next several thousand years. It would carry with it subtle changes in composition and structure caused by its encounter with solar heating and radiation, modifications that might be detectable by hypothetical alien astronomers if 3I Atlas eventually passes through another planetary system. The mathematical precision of orbital mechanics allowed astronomers to predict the visitor's position months in advance, enabling coordinated observation campaigns that would have been impossible with Oumuamua. Ground-based telescopes could be scheduled well in advance. Space missions could theoretically be planned to intercept the object during its closest approach. The European Space Agency even conducted preliminary studies of a rapid response probe that could potentially rendezvous with 3I Atlas during its passage through the inner solar system. As the object continued its approach toward perihelion, its trajectory became a cosmic timeline that connected the present moment to events that occurred when our ancestors were first learning to walk upright on the African savanna. 3 Atlas had been traveling through interstellar space for longer than human civilization had existed, carrying with it samples of materials that predated our species. The path of this particular outsider illuminated the dynamic nature of the galaxy itself. Far from being a static collection of isolated stellar systems, the Milky Way revealed itself as a complex ecosystem where material constantly flowed between stars, carrying information about conditions in distant regions of space and time. Every measurement of 3I Atlas's position and velocity added another data point to humanity's growing understanding of how matter moves through interstellar space. The object's trajectory was more than just a mathematical curiosity. It was a record of galactic history written in the language of celestial mechanics, a story that began millions of years ago around an alien star and would continue long after our own Sun had exhausted its nuclear fuel. The cosmic wanderer continued its billion-year odyssey, temporarily illuminated by our Sun's light, carrying secrets from the depths of space and time that I was only beginning to learn how to read. Part 7. Signals in the Noise. Data from 2 visitors, 3 interstellar visitors, 3 entirely distinct personalities. As 3I Atlas proceeded on its approach through the solar system, astronomers found themselves contrasting its behavior with that of its enigmatic forerunners, looking for patterns that might disclose universal truths about the nature of objects that wander between the stars. The differences were stark and immediately apparent. Whereas Oumuamua had remained stubbornly inactive throughout its transit, displaying no signs of the gas and dust emissions typical of comets. 3I Atlas began outgassing intensely while still beyond the orbit of Jupiter. Its growing coma of sublimated materials formed a hazy envelope approximately 50,000 kilometers in diameter, larger than the planet Mercury. Oumuamua, I. Borisov, discovered in 2019, had represented a middle ground between these two extremes. That visitor had acted like a relatively standard comet, complete with the characteristic tail of gas and dust heated by solar radiation. But its chemical composition showed unusual properties, concentrations of carbon monoxide that were 10 to 50 times higher than anything found in our solar system's comets. Dr. Alan Fitzsimmons from Queen's University, Belfast, who had examined all three visitors, captured the scientific community's confusion. It is like getting 3 postcards from different countries, written in completely different languages, but all claiming to describe the same fundamental experience of travel. The morphological differences were profound. Oumuamua's extreme elongation, possibly 10 times longer than its width, had no equivalent among objects in our solar system. Its tumbling rotation and mysterious acceleration are still unexplained. Despite years of analysis, computer models have difficulty identifying any natural process that could create such an unusual shape while preserving its structural integrity over millions of years of interstellar travel. 3I Atlas, in contrast, appeared refreshingly conventional in its basic geometry. Light curve analysis suggested a roughly spherical nucleus with only slight elongation, perhaps 1.5 to 2 times longer than its width. Its rotation period of approximately 29 hours was consistent with what one would expect from a typical comet, and its axis of rotation remained stable rather than tumbling chaotically through space. The chemical signatures told equally varied stories. Spectroscopic analysis of 2I Borisov had revealed water vapor, carbon monoxide, and cyanide, a composition broadly similar to comets from the outer regions of our solar system, but with significant differences in ratios and concentrations. The object had clearly formed in the cold outer regions of an alien planetary system, probably around a star similar to our Sun. 3I Atlas exhibited yet another chemical personality. Its spectrum showed strong signatures of silicate minerals, suggesting a rocky core covered with volatile ices. The isotope ratios of hydrogen, oxygen, and carbon differed measurably from solar system values, indicating formation around a star with a different metallicity and evolutionary history. Most intriguingly, organic compounds detected in the object's coma included complex molecules that had been modified by millions of years of cosmic ray bombardment. The rotation characteristics provided additional insights into each object's history and structure. Oumuamua's chaotic tumbling suggested either a recent violent collision or an internal structure that deviated significantly from simple assumptions about homogeneous density. The 8-hour rotation period was unusually fast for such an elongated object, requiring either exceptional material strength or internal support structures. Oumuamua, I. Borisov had shown a more conventional rotation period of roughly 7 to 8 hours, with variations in brightness that suggested an elongated but not extremely distorted shape. The object's behavior had been predictably comet-like throughout its passage through the solar system. 3I Atlas fell between these extremes with its 29-hour rotation period and relatively stable axis orientation. The slower rotation suggested either a larger size or a more structurally robust construction than its predecessors. Subtle variations in outgassing rates, synchronized with the rotation period, indicated that volatile materials were not uniformly distributed across the surface, a characteristic that might preserve information about the object's formation environment. The outgassing behaviors provided perhaps the most dramatic contrasts between the three visitors. Oumuamua's lack of any detectable coma or tail had been one of its most puzzling characteristics. Despite approaching to within 0.25 astronomical units of the Sun, close enough to vaporize water ice and other volatiles, the object had remained stubbornly inert. This apparent absence of volatile materials had contributed to speculation about artificial construction or exotic composition. 2I Borisov had displayed vigorous outgassing throughout its passage, creating spectacular tails visible to amateur telescopes and providing abundant material for spectroscopic analysis. The comet's activity had peaked during its closest approach to the Sun and gradually declined as it moved back toward interstellar space, exactly the behavior predicted by theoretical models. 3I Atlas represented yet another variation on the theme. Its outgassing had begun at unusually large distances from the Sun, suggesting either a composition dominated by extremely volatile materials or a surface structure that facilitated rapid sublimation. The coma displayed complex temporal variations that did not correlate simply with solar heating, hinting at internal processes or structural complexities not seen in typical comets. The speed differences among the three visitors provided clues about their respective origins and ejection mechanisms. Oumuamua's approach velocity of approximately 26 kilometers per second suggested a relatively gentle ejection from a nearby stellar system, possibly through gravitational interactions with giant planets. 2I Borisov's intermediate velocity of around 32 kilometers per second implied either a more distant origin or a more energetic ejection process. 3I Atlas's extreme approach velocity of 61 kilometers per second required either ejection during a catastrophic event, such as a stellar explosion or a close encounter with a massive object, or acceleration over vast distances during an extraordinarily long journey through interstellar space. The high velocity suggested origins in regions of the galaxy with different stellar dynamics than our local neighborhood. Population statistics derived from the three discoveries painted an intriguing picture of the interstellar medium. The rate of detection implied that analogous objects journeyed through the inner solar system multiple times every 10 years, with the majority evading discovery on account of their diminutive size or disadvantageous viewing angles. Projecting this frequency across the entire galaxy suggested a colossal population of meandering debris, possibly amounting to trillions of bodies larger than 100 meters adrift between stellar systems. The variety in characteristics observed in just three such objects hinted at a far wider array of properties within the greater population. Computational models anticipated that forthcoming surveys could identify visitors spanning from minuscule rocky pieces to immense ice spheres hundreds of kilometers across. Some could represent untouched samples of primordial solar system material, while others might be heavily altered remnants from stellar detonations or planetary impacts. Dr. Robert Warwick, who held the unique honor of discovering two of the three verified interstellar visitors, contemplated the ramifications. We have progressed from 0 to 3 discoveries in under a decade. Every single one has been entirely distinct from the others, which points to a total population that is immensely more varied than we had ever conceived. We are gathering samples of objects from all corners of the galaxy, each bearing its own singular narrative of creation, evolution, and expulsion. The collective dataset from all three visitors was already fundamentally altering theoretical models of planetary system formation and evolution. The chemical variations showed that stellar systems throughout the galaxy had undergone diverse evolutionary paths, with differing modes of planet formation, migration, and disruption. The range of ejection speeds indicated that numerous mechanisms were at play in populating interstellar space with debris. Perhaps most telling, the consistent arrival rate suggested that the exchange of material between stellar systems was a continuous process, not an infrequent catastrophic occurrence. The galaxy was showing itself to be a dynamic ecosystem where matter perpetually circulated between stars, transporting information about conditions in remote expanses of space and time. As 3I Atlas proceeded on its trajectory toward the Sun, contributing daily to the expanding database of interstellar visitor attributes, one reality became ever more apparent. These three objects were just the start of a much more extensive story. The void between stars was not vacant, but was instead populated by innumerable emissaries carrying specimens from every region of the galaxy. Each subsequent detection would contribute another fragment to the puzzle, progressively uncovering the true essence of interstellar space and our solar system's position within the wider galactic community. Part 8. The Probability Problem. The mathematical findings were disquieting. That was the delicate manner in which astronomers characterized the widening gap between theoretical forecasts and observed fact. Prior to Oumuamua's unforeseen arrival in 2017, the most advanced models forecasted that observable interstellar objects should traverse the inner solar system, perhaps once in a century, if we were exceptionally fortunate. 3 confirmed discoveries in fewer than 8 years indicated those models were off by factors of 10 to 100. Dr. Alan Stern of the Southwest Research Institute had dedicated decades to honing calculations regarding interstellar object populations. His pre-2017 projections, which were deemed optimistic at that time, anticipated roughly 1 discovery per decade with the most sensitive survey telescopes available then. We were not merely mistaken, he conceded during a 2025 conference talk. We were astonishingly, shamefully mistaken. The issue was rooted in core assumptions about the processes by which planetary systems form, develop, and eventually cast out material into interstellar space. Conventional models posited that such expulsion events were relatively infrequent, happening mainly during the late heavy bombardment phase when giant planets shifted to their present orbits. These computations suggested that most stellar systems would add only negligible quantities of debris to the interstellar medium, but the rate of discovery implied something much more dramatic. Either expulsion events were significantly more frequent than anticipated, or the effectiveness of these events in creating detectable debris was profoundly underestimated. The consequences reached well beyond the field of astronomy. They pertain to foundational inquiries about the structure and evolution of the galaxy as a whole. The updated projections were mind-boggling. If Oumuamua, 2I Borisov, and 3I Atlas constituted a representative sample of the interstellar object population, then our solar system ought to be encountering dozens of comparable visitors annually. The majority would be too small, too dim, or too poorly positioned for detection with existing technology. But a considerable portion should be accessible to next-generation survey instruments. Extrapolating this to the entire galaxy yielded figures that defied belief. The Milky Way could harbor trillions of interstellar objects exceeding 100 meters in diameter, drifting between stellar systems in a vast web of gravitational interactions. This unseen population would signify a previously unrecognized element of galactic mass, potentially rivaling the combined mass of all planets in all stellar systems. The detection data presented further enigmas. All 3 confirmed interstellar visitors had been found by comparatively small, ground-based telescopes running automated survey programs. This implied that larger, more advanced instruments might find such objects on a routine basis, perhaps several times a year, once dedicated search initiatives became fully active. Dr. Robert Jedicke from the University of Hawaii, who specialized in solar system population statistics, outlined the implications. We are like individuals who searched for rare birds for years and never saw a single one. Then we suddenly saw 3 distinct species in 1 week. Either we became phenomenally lucky, or these supposed rare birds are in fact ubiquitous, and we simply did not know where to search. The probability computations grew progressively more intricate when factoring in observational biases. Interstellar objects were most readily found when their paths brought them relatively near to Earth, and when they were traveling slowly enough for multiple observations. Objects arriving from specific directions could be masked by the brightness of prominent stars or hidden by the plane of the Milky Way. Monte Carlo simulations were used to try and model these selection biases, creating millions of hypothetical interstellar visitors with randomized characteristics and paths, and then assessing what portion would be observable by current survey programs. The outcomes consistently showed that the observed detection rate could be accounted for only if the actual population was orders of magnitude greater than previously thought. The source of this immense population was still a mystery. Prevailing theories for planetary system formation projected ejection rates that were not sufficient to populate interstellar space so thickly. A number of new mechanisms were put forward to explain the inconsistency. Close stellar encounters might be more disruptive than previously thought. When stars pass within a few thousand astronomical units of one another, which happens approximately once every few million years for a typical stellar system, the gravitational disturbances could eject not just single objects, but entire populations of comets and asteroids. Binary star evolution offered another possible source of interstellar debris. Roughly half of all stars reside in multiple star systems, where intricate gravitational interactions during stellar evolution could upset planetary orbits and expel material at great speeds. The dissolution of wide binary systems could scatter debris over vast stretches of interstellar space. More unconventional scenarios included the final throes of massive stars. Supernovae and other stellar explosions could hurl entire planetary systems into interstellar space, generating waves of high-velocity debris that would eventually cross paths with other stellar systems millions of years later. The chemical makeup and extreme velocities of some interstellar visitors lent credence to this idea. The principle of gravitational focusing offered another explanation for the seeming abundance of interstellar objects. The Sun's gravity would deflect the paths of passing objects, directing them toward the inner solar system, where they could be more easily spotted. This focusing mechanism might render our solar system a favored destination for interstellar visitors, leading to an artificially elevated detection rate. Perhaps most compellingly, some scientists suggested that we might be observing the consequences of galactic evolution on much grander scales. The Milky Way's spiral configuration, its bar-shaped central region, and its continuous interactions with satellite galaxies could generate tidal forces that intermittently disrupt stellar systems across the galaxy. These events could happen in cycles spaced by hundreds of millions of years, saturating interstellar space with debris during particular phases of galactic evolution. The timing of humanity's initial interstellar object discoveries prompted further questions. Why were these findings happening now, during the fleeting span of our species' technological advancement? The anthropic principle suggested that this timing might not be a matter of chance. Perhaps we are living in a period of heightened interstellar debris flow, possibly linked to our solar system's current location within the galaxy's spiral structure. Dr. Abraham Loeb from Harvard University, who had emerged as a leading proponent of considering artificial origins for interstellar objects, presented a distinct viewpoint. The sheer number of these visitors might not be a statistical quirk. If technological civilizations are widespread, and if they sometimes dispatch probes or artifacts into interstellar space, then what we are seeing could be a mix of natural debris and artificial envoys. This technological hypothesis was still debated, but the detection statistics offered it some backing. If even a minuscule portion of the presumed interstellar object population was made up of artificial artifacts, the likelihood of detecting such objects during humanity's brief technological age would be markedly increased. The strange characteristics of some visitors, especially Oumuamua's extreme shape and unexplained acceleration, were still not accounted for by standard natural processes. The ramifications went beyond astronomy to astrobiology and the quest for extraterrestrial intelligence. If interstellar space was truly filled with countless wandering bodies, then biological matter might regularly journey between stellar systems, potentially seeding life across the galaxy. Complex organic molecules found in some interstellar visitors supported this idea. The probability issue also had an impact on practical matters of planetary defense. If large interstellar objects were passing through the inner solar system multiple times per decade, then the statistical calculations for impact risks required updating. While the chance of any single object hitting Earth was still exceedingly small, the aggregate risk over geological periods could be greater than previously assumed. As survey telescopes maintained their nightly watch, finding candidate interstellar objects with growing frequency, the true extent of the probability problem became evident. The universe was not the sparse, nearly vacant space between stars that earlier generations had envisioned. Instead, it was revealing itself as a dynamic, teeming environment where material constantly flowed between stellar systems, linking distant worlds through networks of gravitational interaction that spanned millions of years. The laws of chance had been overturned by observation, compelling humanity to face a cosmos far more active and interconnected than we had ever dared to envision. The space between stars was teeming with wanderers, and we were at last learning to discern their signatures amidst the cosmic background. Part 9, the Fermi Paradox Revisited. Where is everyone? Enrico Fermi's renowned question, asked during an informal lunch meeting in 1950, assumed entirely new meanings as humanity contended with the consequences of regular interstellar visitors. If the galaxy was teeming with drifting debris from innumerable stellar systems, why were we not also finding signs of the civilizations that might have produced some of it? The traditional Fermi paradox had always been founded on suppositions of immense, empty voids between stars. The argument was that even if the galaxy hosted millions of technological civilizations, the colossal scale of interstellar space made contact practically unfeasible. Radio signals would diminish to undetectable strengths over such expanses. Physical travel would demand resources and time spans that even advanced civilizations might deem insurmountable. But the discovery of Oumuamua, 2I Borisov, and 3I Atlas had fundamentally changed this view. The space between stars was not vacant, but filled with a perpetual flow of emissaries transporting information between stellar systems. If natural objects could make these journeys with regularity, why couldn't artificial ones? The detection data indicated that objects larger than 100 meters traversed the inner solar system multiple times each decade. Extrapolating to smaller dimensions implied that debris from other stellar systems was constantly falling upon Earth, possibly thousands of tiny pieces each year, most being too small to be detected or to withstand atmospheric entry. This new understanding shifted the Fermi paradox from a question about the lack of signals to a question about the kind of signals we might already be encountering. What if extraterrestrial civilizations had been communicating with us for eons, not via radio waves, but through physical artifacts engineered to endure the voyage between stars? Dr. Abraham Loeb from Harvard University had emerged as the most notable proponent of this viewpoint. We have been scanning the heavens for radio signals for decades, he contended, but we have overlooked the chance that advanced civilizations might favor sending physical messages. A well-crafted artifact could transport far more information than any radio signal, and it would reach its destination with a certain delivery. The idea of interstellar communication through physical objects was not novel. Science fiction had explored such concepts for decades, and serious scientists had occasionally suggested theoretical plans for Bracewell probes, self-reproducing artifacts that could spread throughout the galaxy, carrying information between civilizations. Yet the abundance of interstellar visitors implied that such messaging might be not merely feasible, but common. If every technological civilization now and then sent artifacts into interstellar space, either deliberately or as byproducts of their industrial endeavors, then the galaxy could be filled with artificial messengers, just waiting to be found and understood. The difficulty was in telling artificial objects apart from natural ones. Oumuamua's peculiar characteristics had ignited a fierce debate about its potential artificial origin. Its extreme shape, mysterious acceleration, and absence of detectable outgassing were challenging to account for through natural processes alone. Nevertheless, the scientific community had generally favored exotic, yet natural explanations over considering a technological source. This opposition to artificial explanations was a reflection of deep-seated biases in scientific culture. The principle of Occam's razor suggested that natural explanations should be favored over more intricate artificial ones. The standard of proof for extraordinary claims, such as finding alien technology, was set justifiably high to guard against false positives and uphold scientific integrity. But the statistical abundance of interstellar visitors was compelling a reevaluation of what was the simpler explanation. If such objects were rare natural events, their discovery during humanity's short technological era would be an incredible coincidence. If they comprised artificial artifacts from technological civilizations, their prevalence during our era of detection might be less of a surprise. The timing argument was especially persuasive. Humanity has possessed the ability to detect interstellar objects only in the last few decades. The fact that we found 3 such objects in our initial 8 years of systematic searching pointed to either exceptional luck or a population density much greater than predicted by natural processes alone. Dr. Avi Loeb worked out the probabilities. If interstellar objects like Oumuamua are entirely natural phenomena with the abundance suggested by our detection rate, then the chance of humanity finding them during our brief technological period is about 1 in 10,000. Such coincidences can happen, but they should prompt us to explore other explanations. The search for extraterrestrial intelligence had already started to adjust to these new possibilities. Radio telescopes now regularly scanned newly found interstellar objects for any indication of artificial signals. Optical observatories looked for unusual reflection patterns that might suggest manufactured surfaces. Even gravitational wave detectors were being considered as instruments for spotting very massive artificial objects. The European Space Agency had put forward an ambitious plan to intercept the next suitable interstellar visitor with a high-speed probe capable of in-depth analysis. Such a mission could ascertain whether seemingly natural objects concealed artificial components, embedded computers, communication systems, or even biological samples from their home civilizations. The implications reached beyond the search for existing civilizations to questions about the archaeological history of galactic intelligence. If technological species had been launching artifacts into interstellar space for millions of years, then some of these messengers might be the only surviving remnants of long-gone civilizations. The galaxy could be filled with the technological fossils of species that had emerged and vanished long before our Sun was even formed. This galactic archaeology viewpoint implied that interstellar objects might hold information about the long-term evolution of intelligence in the Milky Way. Artificial artifacts could contain data on the technologies, cultures, and eventual destinies of civilizations that existed billions of years in the past. The chemical and structural analysis of such objects could reveal patterns in how intelligence arose and dispersed throughout the galaxy. The concept also brought up questions about humanity's own additions to interstellar debris. Our activities in space were already producing artifacts that would one day escape the solar system and drift among the stars. The Voyager probes, New Horizons, and various other spacecraft would become Earth's first interstellar envoys, carrying information about our civilization to whatever intelligence might one day find them. More troublingly, human space activities were also creating a substantial amount of debris that could eventually make its way into interstellar space. Used rocket stages, inactive satellites, and pieces from orbital collisions could join the galactic population of wandering objects. Future archaeologists examining debris from our stellar vicinity might determine that 21st century Earth was inhabited by a wasteful, short-sighted species that contaminated even the space between stars. The philosophical ramifications were immense. If the galaxy was indeed filled with artificial messengers from countless civilizations, then the Fermi paradox might be solved not by the lack of extraterrestrial intelligence, but by our inability to perceive its presence. The answer to "where is everybody" might be all around us, in forms we are just starting to comprehend. This perspective suggested that the search for extraterrestrial intelligence must broaden far beyond radio astronomy to encompass the systematic investigation of interstellar visitors. Every object entering our solar system from interstellar space was a potential message from another world, encoded in its structure, composition, trajectory, and behavior. The task was to create the tools and methods to decode such messages. Unlike radio signals, which were intended to be clearly artificial, physical artifacts from alien civilizations might be designed to look natural to evade detection by hostile intelligences. The difference between advanced technology and exotic natural phenomena could be slight enough to elude current analytical techniques. As surveys kept finding new interstellar visitors with increasing frequency, the updated Fermi paradox became a matter not of silence, but of interpretation. The galaxy might be in constant communication with us through physical messengers that we were only beginning to recognize and comprehend. The cosmic solitude that had defined humanity's view of the universe since the scientific revolution was yielding to a growing realization of our involvement in a vast ancient network of material exchange between stellar systems. Whether that network included deliberate messages from other intelligences was still an open question, but the possibility was reshaping both our search methods and our core assumptions about our place in the cosmos. The answer to Fermi's question might be, they are here. We are just now learning how to see them. Part 10. Theories and Tensions. The coffee had turned cold hours before, but Dr. Sarah Chen kept her gaze fixed on the data flowing across her screen at the Jet Propulsion Laboratory. The most recent spectroscopic readings of 3I Atlas revealed something that should not exist. Isotope ratios that contradicted every model of stellar nucleosynthesis she could bring to mind. Either the object originated under conditions unlike any other in the known universe, or the models themselves required a fundamental overhaul. The scientific community's reaction to the growing number of anomalies in interstellar visitor data had split into increasingly solidified factions. On one side were the methodological traditionalists, who maintained that natural explanations had to be fully explored before considering more unconventional possibilities. On the other was an expanding group of scientists who contended that the mounting evidence necessitated the consideration of hypotheses that earlier generations would have brushed aside as science fiction. The discussion had become especially heated concerning Oumuamua's enduring puzzles. 8 years after its discovery, the object's extreme shape and mysterious acceleration were still not accounted for by any plausible natural mechanism. Computer simulations had examined every imaginable formation scenario: tidal disruption near massive stars, collisional fragmentation in dense stellar clusters, unusual sublimation processes. Yet none could explain all of the object's observed characteristics. Dr. Alan Fitzsimmons from Queen's University, Belfast, one of the most esteemed figures in asteroid and comet research, stood by the traditionalist viewpoint. Science advances by discovering natural explanations for natural events. The history of astronomy is filled with puzzling objects that seem to demand outlandish explanations until we gained a better understanding. Oumuamua may be peculiar, but peculiar is not the same as artificial. The natural explanation faction had converged on progressively more complex models. Perhaps Oumuamua was made of solid hydrogen, sublimating so gradually that its outgassing was invisible to our instruments. Maybe it was a piece of a nitrogen iceberg, akin to the surface composition of Pluto, but cast into interstellar space by some cataclysmic event. These explanations demanded exotic conditions and materials, but they stayed within the confines of established physics and chemistry. The artificial hypothesis faction, spearheaded by Dr. Abraham Loeb, argued that the natural explanations had grown so elaborate that they were more of a strain on credibility than the technological alternative. When you have to resort to invisible outgassing, exotic materials not found anywhere else in the solar system, and formation mechanisms that have never been witnessed, Loeb contended, perhaps it is time to entertain the idea that we are observing technology. The debate had taken on philosophical aspects that reached far beyond the particular case of any single object. It touched on fundamental questions about the nature of scientific investigation, the burden of proof for extraordinary assertions, and the function of intellectual conservatism in preventing both erroneous discoveries and genuine advancements. Dr. Michelle Bannister from the University of Canterbury offered a middle ground perspective. The real question is not whether a specific object is natural or artificial. The issue is that we are observing phenomena we do not comprehend, which signifies that our models of planetary formation, stellar evolution, and interstellar chemistry are lacking. Whether the solutions involve exotic natural processes or extraterrestrial technology, we are clearly overlooking something significant. The tensions had been intensified by the media's handling of interstellar visitor discoveries. Headlines proclaiming alien probe and visitors from space had pushed scientists into defensive stances, stressing conventional explanations to fend off accusations of sensationalism. This defensive attitude had fostered an atmosphere where researchers were hesitant to discuss artificial possibilities, even in private. The situation had historical parallels. In the initial days of pulsar astronomy, the remarkably consistent radio signals from these objects were dubbed LGMs, for little green men, because no known natural process could create such precise timing. It was only after finding multiple pulsars with similar traits that astronomers felt certain they were observing a new kind of stellar remnant rather than alien technology. But the interstellar visitor case was complicated by the object's fleeting nature. Unlike pulsars, which could be observed repeatedly over years or decades, interstellar objects offered only brief periods for thorough study. Oumuamua was observable for just a few weeks before it dimmed beyond the reach of Earth's most powerful telescopes. This time limitation made it exceptionally hard to collect the comprehensive data required to settle disputes about the object's nature. The scientific culture itself had become a part of the issue. Peer review systems tended to favor gradual progress in understanding over revolutionary shifts in thinking. Grant-making bodies were unwilling to finance research into exotic explanations as long as more conventional options remained unexamined. Career progression hinged on publishing findings that built logically on prior work rather than questioning core assumptions. Young researchers found themselves trapped between conflicting pressures. The most captivating and potentially career-making discoveries were in exploring unconventional explanations for anomalous data. But the most secure route to academic success was to work within established paradigms, even when those paradigms had difficulty explaining the observations. Dr. Jennifer Bergner from UC Berkeley, whose work centered on the chemistry of interstellar objects, articulated the predicament. I have witnessed junior faculty members censoring their own hypotheses because they fear being branded as fringe scientists. We are fostering an environment where the most critical questions cannot be debated openly for fear of damaging someone's professional standing. The global nature of modern astronomy introduced another level of complexity. Scientists from various nations brought different cultural perspectives on unconventional ideas. European researchers generally leaned toward more conservative interpretations. While American scientists were more inclined to speculate publicly about exotic possibilities, Asian astronomers often acted as mediators between these differing styles. Social media had magnified these cultural divides, enabling discussions that might have once been limited to scientific conferences to spill into public arenas. Twitter discussions about Oumuamua's artificial origin attracted thousands of retweets, whereas meticulous analyses of natural formation mechanisms gained little notice outside of professional circles. The polarization had tangible effects on observational programs. Telescope time allocation committees had to choose between proposals that presupposed conventional explanations and those that were explicitly looking for signs of artificial origin. Some institutions developed unofficial policies against funding research that specifically sought evidence of extraterrestrial technology, choosing instead to back investigations that could yield publishable results regardless of their conclusions. The debate had also highlighted interesting generational gaps within the astronomical community. Seasoned researchers who had established their careers on conventional models tended to oppose explanations that could undermine decades of earlier work. Younger scientists, with less at stake in existing paradigms, were more receptive to revolutionary ideas. Dr. Robert Warwick, who had found both Oumuamua and 3I Atlas, was in the unique situation of having discovered phenomena that contradicted his own theoretical predictions. Quote, "When you dedicate your career to searching for conventional asteroids and comets, and then you suddenly find objects that do not conform to any known category, it compels you to re-examine everything you believed you understood about the solar system." The growing body of data from multiple interstellar visitors was gradually altering the parameters of the debate. Each new discovery imposed further limits on theoretical models, making it progressively harder to devise natural explanations that could account for the complete spectrum of observed characteristics. Yet the same data could also be viewed as proof of a varied population of artificial artifacts with different designs and functions. Perhaps most importantly, the debate was compelling the scientific community to face its own biases and assumptions about what were considered plausible explanations for astronomical phenomena. The line between exotic natural processes and simple artificial ones was proving to be much less distinct than anyone had foreseen. Late-night discussions at astronomical conferences increasingly revolved around questions that would have seemed preposterous just a decade before. How would we identify alien technology if we came across it? What observational signs would differentiate artificial objects from exceptionally unusual natural ones? How should the scientific community act if the evidence for extraterrestrial intelligence became undeniable? These were not merely theoretical questions. As survey telescopes kept finding new interstellar visitors with growing frequency, astronomers were analyzing data that challenged fundamental assumptions about the nature of matter, the evolution of planetary systems, and humanity's position in the cosmic hierarchy. The theories and tensions surrounding interstellar visitors were reflections of deeper uncertainties about the universe we live in. Whether the answers were found in exotic physics or extraterrestrial technology, one thing was becoming evident. The cosmos was far more strange and dynamic than the tidy theoretical models of previous generations had indicated. The debate raged on in laboratories and conference halls worldwide. But beyond those fervent discussions, the objects themselves carried on with their ancient travels through interstellar space, holding secrets that humanity was only just starting to learn how to unlock. Part 11. The next discovery could change everything. The future of interstellar visitor detection was materializing ahead of schedule, high in the Chilean Andes, where the Vera C. Rubin Observatory was concluding its final calibrations months sooner than anticipated, propelled by the pressing need to catalog the cosmic envoys passing through our solar system. Once fully active, this technological wonder would transform our capacity to find and examine visitors from other star systems. The observatory's 8.4-meter mirror and 3 billion pixel camera would survey the entire visible sky every 3 days, producing approximately 20 terabytes of data each night. More significantly, it would achieve this with unparalleled sensitivity, capable of spotting objects as faint as the 24th magnitude, about 40 million times dimmer than the faintest stars observable with the naked eye. Dr. Mario Jurek, who was in charge of the observatory's data management systems, described the shift this would bring. We are moving from possibly catching one interstellar visitor per decade to potentially finding dozens each year. Instead of rushing to study objects as they depart the solar system, we will be monitoring them from the moment they enter. The consequences were immense. Current detection techniques depended on luck and favorable positioning. Objects needed to pass relatively near Earth while being bright enough for existing surveys to spot them. The Rubin Observatory would cast a much broader net, discovering visitors while they were still on their way to the inner solar system, and giving months or even years of early warning before their nearest approach. But finding these cosmic wanderers was only half the battle. The true transformation would stem from the observatory's ability to characterize large populations of interstellar objects, uncovering patterns that single discoveries could never reveal. Statistical analysis of hundreds or thousands of visitors would finally resolve fundamental questions about their origins, compositions, and the processes that launched them from their home star systems. Artificial intelligence systems were being created specifically to identify the faint signatures of interstellar motion among the billions of moving objects the observatory would spot each night. Machine learning algorithms, trained on simulated data, would learn to differentiate hyperbolic trajectories from the elliptical orbits of standard solar system objects, flagging potential interstellar visitors within hours of their initial detection. The European Space Agency was setting up complementary systems to automatically initiate follow-up observations at telescopes around the globe. Within minutes of verifying a new interstellar visitor, observatories on multiple continents would launch coordinated efforts to measure its spectrum, rotation, and detailed characteristics before it faded beyond the detection limit. NASA's Jet Propulsion Laboratory had advanced the preparations even further, creating rapid-response spacecraft concepts that could potentially intercept especially interesting visitors. The designs employed solar sail technology and gravitational slingshot maneuvers to reach the extreme speeds required to overtake objects moving at dozens of kilometers per second relative to the Sun. Dr. Julie Castillo-Rogez, who was in charge of the interceptor mission studies, detailed the technical hurdles. We are discussing the pursuit of objects that are traveling faster than anything we have ever attempted to intercept. The spacecraft would have to be pre-positioned in specific orbits, awaiting suitable targets, and then perform complex maneuvers with virtually no room for error. The potential scientific rewards warranted these extreme efforts. Direct sampling of an interstellar visitor's material would offer definitive proof of its origin and composition. Microscopic examination could reveal information about formation conditions in alien planetary systems, the consequences of millions of years of cosmic ray exposure, and possibly even preserved biological matter from other worlds. But perhaps the most compelling possibility was the chance of discovering something that could not be explained by natural means. The statistical prevalence of interstellar visitors suggested that if even a minuscule portion were artificial artifacts, future surveys should find them regularly. Unlike the present situation, where single anomalous objects spark endless debate, clear patterns in the data might furnish convincing evidence of extraterrestrial technology. The search methods were broadening beyond conventional optical astronomy. Radio telescope arrays were being programmed to automatically scan newly found interstellar objects for any signs of artificial signals. The techniques developed for SETI research, looking for patterns that suggest intelligent origin, would be applied to every visitor that entered our cosmic vicinity. Infrared space telescopes provided another path for discovery. Artificial objects might possess thermal signatures that were different from natural ones, especially if they had internal heat sources or unusual surface materials. The James Webb Space Telescope had already proven its capability to study solar system objects in unprecedented detail, and similar methods could be applied to interstellar visitors. Even more unconventional detection methods were being investigated. Gravitational wave observatories could potentially be sensitive to the passage of very massive interstellar objects, particularly if they had unusual internal structures. Neutrino detectors might be able to identify visitors that contained radioactive materials or even artificial power sources. The implications reached beyond detection to matters of planetary defense. While the likelihood of any single interstellar object hitting Earth was still exceedingly small, the discovery that such objects were far more common than previously thought had led to new risk evaluations. Computer simulations indicated that large interstellar impactors might strike once every few million years, rare enough to be largely disregarded on human timescales, but frequent enough to have shaped Earth's biological history over geological time. More worrisome was the possibility of finding an artificial object on a collision course with Earth. While such a scenario was purely hypothetical, it had triggered initial talks about how humanity should react to clear proof of extraterrestrial technology, especially if that technology presented a potential danger. The discovery protocols were being updated to address these possibilities. Plans were devised for immediate international consultation if any interstellar visitor showed unambiguously artificial traits. The procedures were similar to those for potential asteroid impact scenarios, but with added considerations for the chance that the object might be under some form of intelligent control. Academic institutions were launching new research programs focused on interstellar visitor studies. Graduate students could now specialize in a discipline that did not exist a decade ago, analyzing data from objects that came from around alien stars. The curriculum encompassed not only astronomy and planetary science, but also astrobiology, material science, and even archaeology, skills that might be required to interpret artifacts from extraterrestrial civilizations. International collaboration was growing swiftly. The European Space Agency, NASA, the Japanese Space Agency, JAXA, and other bodies were coordinating their future missions to provide comprehensive coverage of interstellar visitor discoveries. Bilateral agreements set up protocols for sharing data and coordinating observations, viewing interstellar objects as a shared scientific asset for all of humanity. Private space companies were also contributing to the effort. Several firms had revealed plans to create specialized spacecraft for intercepting and examining interstellar visitors. The potential commercial worth of such missions was uncertain, but the scientific prestige and technological challenges drew considerable investment. The legal ramifications were intricate and without precedent. International space law had never considered the scenario of studying material that originated in other star systems. Questions emerged about ownership rights, contamination protocols, and the duties of different nations if artificial objects were found. Legal experts were crafting frameworks for interstellar visitor governance, though they conceded that the law would probably trail behind the discoveries. Cultural and philosophical preparations were perhaps just as crucial. Humanity's first confirmed encounter with material from another star system had already tested our sense of cosmic solitude. Future discoveries could compel even more profound reassessments of our place in the universe, especially if artificial objects were found to be common. Religious and philosophical communities were starting to address the implications of regular contact with extraterrestrial materials. While the objects themselves might be inanimate, they signified tangible links to other worlds and possibly other forms of intelligence. The psychological and cultural effects of such discoveries were largely uncharted territory. As survey telescopes kept up their nightly vigils, searching the sky for the telltale motion patterns of interstellar visitors, the feeling of anticipation within the scientific community was almost tangible. The next major discovery could be months or years away, but it felt unavoidable. The universe had already shown that it was far more dynamic and interconnected than previous generations had believed. The question was not if humanity would find more interstellar visitors, but what those encounters would tell us about the nature of planetary systems, the prevalence of life in the galaxy, and the possibility that intelligence might be a common rather than an exceptional phenomenon. The future was approaching at 50 kilometers per second, bringing with it answers to questions we were only just learning how to formulate. Part 12. Closing the Loop. The streams of data are incessant. Tonight, as you drift into sleep, robotic telescopes on 6 continents are gathering photons that departed from distant stars millions of years ago. Amidst those ancient specks of light, algorithms are hunting for the slight movement that reveals visitors from other worlds. The cosmic emissaries persist on their billion-year voyages, unconcerned with our newly acquired capacity to perceive their transit through our small section of space. I began this narrative with a straightforward observation, an object not gravitationally tied to our sun passing through our cosmic neighborhood. Now, after tracing the evidence through 8 years of discovery and debate, I find myself facing a universe that declines to adhere to our preconceptions. The expanse between stars is not the vacant emptiness our forebears conceived, but a thoroughfare traveled by wanderers bearing messages we are only just starting to decode. 3 confirmed visitors. Oumuamua, with its unfeasible shape and enigmatic acceleration, tumbling through the darkness toward Pegasus. Borisov, reassuringly comet-like yet chemically alien, leaving a trail of exotic vapors from a world we will never behold. And 3I, Atlas, approaching even now, carrying the promise of answers and the certainty of new questions. Each object has tested our comprehension in different respects. Each has compelled us to broaden our idea of what exists in the cosmos and how often it pays a visit to our vicinity. Yet, despite all their variations, they convey a shared message. The galaxy is vastly more active and interconnected than we ever dared to conceive. The mathematics tell a story that our intuition finds hard to grasp. If these 3 discoveries are indicative of a typical sampling rate, then dozens of similar objects traverse our solar system annually. Most go unseen by our instruments, being too small, too dim, or too unfavorably positioned for detection. But they are present, bringing with them samples from every kind of star system, every era of galactic evolution, and every process that can launch matter between the stars. This realization reshapes our understanding of Earth's position in the cosmic hierarchy. We are not isolated inhabitants of a closed system, shielded from external influence by vast distances and empty space. We are participants in a galactic ecosystem that has been delivering samples to our planet for billions of years. The materials that constituted our world include contributions from stellar systems throughout the local region of the Milky Way. The consequences ripple through every scientific field. Planetary formation models must now consider routine contamination by interstellar materials. The origin of life on Earth might be linked to organic compounds that endured journeys between stars. The evolution of our solar system has been shaped by occasional visitors carrying momentum and energy from distant worlds. But perhaps the most profound consequence relates to the Fermi paradox and humanity's quest for signs of extraterrestrial intelligence. The space between stars is not silent and empty, but filled with physical emissaries that could transport information more dependably than any radio signal. If technological civilizations are present elsewhere in the galaxy, they might choose to communicate through artifacts engineered to survive million-year journeys between stellar systems. The debate over Oumuamua's potential artificial origin highlighted the difficulties we encounter in identifying such messages. The line between exceedingly unusual natural phenomena and relatively simple artificial objects may be far less distinct than we imagine. Our current analytical methods, created for studying conventional solar system objects, may be insufficient for identifying technology designed by non-human intelligence. This uncertainty compels us to face uncomfortable questions about our preparedness for contact with extraterrestrial civilizations. If alien artifacts are already passing through our solar system, indistinguishable from exotic natural objects to our current level of analysis, then we may be failing to see the very evidence we profess to be searching for. The scientific community's reaction to these possibilities has shown both the strengths and weaknesses of our collective method for dealing with unprecedented phenomena. The methodological conservatism that shields us from false discoveries may also prevent us from seeing genuinely revolutionary developments. The peer review systems that guarantee rigorous analysis may also stifle the investigation of ideas that challenge fundamental assumptions. Nevertheless, the system is adapting. Funding bodies now provide support for research into interstellar visitor detection and characterization. New telescopes are being designed specifically to find and study objects from other star systems. International protocols are being created to coordinate responses to particularly unusual discoveries. The technological revolution is already in progress. The Vera C. Rubin Observatory will soon be surveying the entire sky every few nights, finding dozens of interstellar visitors each year instead of the few we have found thus far. Artificial intelligence systems will identify their signatures within hours of initial detection. Rapid response protocols will initiate coordinated observations across the globe. For the first time in human history, we are getting ready to study material from other star systems as a routine scientific endeavor, not as an extraordinary occurrence. Graduate students are specializing in interstellar visitor analysis. Research programs are being set up at major universities. New scientific journals are being launched to publish the expanding volume of research. The cultural shift may be just as important. Humanity is gradually coming to terms with the reality of existing within a galaxy that actively delivers samples from other worlds. The psychological isolation that defined our species for most of its history is yielding to a growing sense of cosmic connection. This change is quickening as detection rates climb. The discovery of 3I Atlas caused less media frenzy than Oumuamua's arrival, but generated deeper scientific excitement. We are getting used to the notion that our solar system has regular visitors, even as we grapple with understanding what their presence signifies. The next chapter of this story is already being written in the data flowing from telescopes around the world. Statistical analysis of larger samples will uncover patterns not apparent in single discoveries. Detailed studies of composition and structure will shed light on the conditions that prevail around other stars. Direct sampling missions may finally give definitive answers to questions about the object's origins and nature. But despite all our technological preparations and scientific protocols, the most significant discoveries may be those that force us to discard our current paradigms entirely. The universe has already shown its ability to astonish us. The objects journeying between stars may carry messages encoded in ways we have not yet learned to decipher. As you close your eyes tonight, think about the vast networks of matter flowing through interstellar space, pieces thrown out by dying stars, debris scattered by planetary impacts, materials shaped by gravitational chaos around alien worlds. All of it in motion, following paths that cross and diverge over millions of years, sometimes delivering samples to planetary systems like our own. Some of these wanderers might carry the chemical signs of life from distant worlds. Others could hold information about stellar evolution in parts of the galaxy we will never directly see. A few could be artifacts made by intelligence we have not yet learned to identify. The cosmic emissaries continue their ancient journeys, indifferent to our theories and expectations. They carry with them the stories of worlds beyond our imagination, written in the language of physics and chemistry, geology, and perhaps biology. We are finally learning to read these messages, though we understand only the initial few words of what may be vast libraries of information. Oumuamua is speeding through the outer solar system, tumbling toward interstellar space at nearly 40 kilometers per second. In about 20 years, it will pass within a few light-years of the star system, Ross 248. If that system hosts intelligence, they might detect this visitor from our cosmic vicinity and wonder, as we have wondered, about its origin and significance. 3IR Atlas nears its October rendezvous with the Sun, growing steadily brighter as volatile materials turn to gas on its surface. Telescopes worldwide monitor its advance, measuring properties that will illuminate conditions around the distant star where it formed millions of years ago. And somewhere in the blackness beyond our ability to detect, the next messenger is already on its way. Its path was determined by events that happened before our species came to be, carrying it across immense distances to this exact moment in space and time when humanity has at last acquired the ability to perceive its arrival. The age of interstellar visitors has commenced. We are no longer alone in this region of space, no longer isolated observers of a remote cosmos. We are participants in a galactic community that communicates through wandering messengers, connected to every star system through networks of gravitational interaction that span millions of years. And so the only question that is left is what else is already on its way.